I am Dr. W.B. Gulmale from Kamla Nehru Mahavidyalaya, Nagpur. Today we are discussing the method of determination of stability constant by using mole ratio method. As we know, there are different methods to determine the stability constant of the complexes. Job method of continuous variation already we have discussed. Second method is a mole ratio method, and third one is the Irving-Rossetti method. In case of mole ratio method, this method was given by the James and Tow, and this method is very simple as compared to job method of continuous variation. And important difference, that is the main difference between these two methods, is that the total concentration of the metal is kept constant in mole ratio method. So how to calculate the stability constant for different composition of the complexes? The composition of complex like 1:1 or 1:2 or 2:1, even for 1:3 composition of the complex, we can calculate the stability constant by using mole ratio method. There was an drawback in case of the job method. If the N value is more than 3, that is the ligand value is more than 2, that is 3, for that there is limitations. So up to 2 it is possible, but in case of mole ratio method it is possible to calculate the stability constant for different composition of the complexes. So this method of this mole ratio method, and we are taking an example of FeSSA, sulfosalicylic acid. Iron sulfosalicylic acid is the complex. For this we can determine the stability constant. That detail about this is we are discussing in today's part. So again, today's topic is the metal ligand equilibrium in the solution, and this is the part 4. And in this part we are discussing the method of determination of stability constant by using the mole ratio method. Job method of continuous variation for the determination of stability constant already we have discussed, and this is second method which can be used to calculate the stability constant of the complexes. So this method was given by James and Tow, is the name of scientist, and this method is used to calculate the stability constant of the complexes. And this method is very simple as compared to the job method of continuous variation. So important difference between these two methods is that total concentration of the metal should have to be kept constant in case of mole ratio method. In case of job method, we have taken the different concentration of the metal, but in this case we have to fix the concentration of metal, and therefore in this method the different systems we have to prepare, and different solutions, minimum 10 solutions we have to prepare, and after making these solutions we have to measure the absorbance by using spectrophotometer or by using colorimeter. So how to prepare the system, 10 system or 10 different types of solution? For this case, here it is the composition of the solution of metal, ligand and water are given in the table. So this here we are taking an example of Fe2 phenolphthalein complex. So Fe is a metal, phenolphthalein 110 phenolphthalein or phenolphthalein is a ligand forming the complex Fe2 phenolphthalein. So the solutions we have to prepare 10 solutions, which are how to prepare the system. For the system, tables are given here. This table shows total 10 solutions are there, and in the first, volume of metal ion in the milliliter is shown. This is kept constant. See here, the concentration of the volume, total volume of metal ion is kept constant. So concentration of metal in all the 10 systems are same, 5 ml in all the case. We are changing only the volume of ligand here. See, in first case 1, 2, 3, 4, 5, 6, 7 up to 10. So metal concentration or volume of metal is kept constant. We are changing the ligand volume, and volume to be added. So total volume should be 25 ml. So we have to add here, in case of first we have to add 19 ml. 18. So total is 19, 1, 20 and 5, 25. So total volume should be a 25 ml. So in this way we have to add the water in all the 10 solution: 19, 18, 17, 16, 15, 14, 13, 12, 11 and 10. So that we should obtain we should get the 25 milliliter total volume of the system. So after making all the 10 solutions of this metal ligand, we have to measure the absorbance of all the solution at fixed concentration of lambda max. So mole ratio method, different dilute solutions that we have seen in the table we have to prepare, and which contain the constant volume of metal ion and shows different concentration of ligand, that is complexing agent like phenolphthalein, and the ratio of concentration should be vary 1:10 ratio of metal ligand. So metal ligand ratio should be 1:10 ratio of metal ligand. So first of all we have to find out the maximum absorbance, that is known as lambda max. First of all, by taking any one solution out of 10, we have to find out the lambda max, that is maximum absorbance, and we have to record the absorbance of all the 10 solutions at this lambda max. And absorbance of, as we know, absorbance are proportional to the equilibrium constant concentration of the metal ion present in the solution. Therefore we have to plot a graph between absorbance versus ratio of mole of the ligand to the mole of the metal, and this plot is shown in this figure. So after first of all we have to measure the lambda max, and at this lambda max we have to measure the absorbance of all the 10 solutions, and after that we have to plot the graph between the absorbance versus ratio of mole of ligand to the mole of metal, and the graph shown here in this slide. So here is on this axis absorbance is taken, and here mole ratio, concentration of metal upon concentration of ligand, or concentration of ligand upon concentration of metal. We obtain, this is the nature of curve. In this case obtain it increases, see slight change, turn is there, and now here increases and now become constant. From this graph we have to find out the value of AM and A0. That is here, this is known as the AM and A0. So ES and EM, this value is a delta shown. This is the ES value and this is the EM value. How can we find out ES and EM? Now see here, this take the scale, and here now the it turns, the curve turns and become constant. So make the line from this constant part here on the y-axis. This constant value to this y-axis give the value of ES, and EM value is obtained from which is show the turn. So it is increases and then slight turn is there. So where it start turn, the point at which it start turn is known as the EM. So EM and ES value obtained from this graph, which are useful to calculate the values shown here, alpha, that is degree of. So for this case we have to consider the formation of complex between metal and ligand in the ratio 1:n. So the metal ligand ratio should be 1:n. 1 is there because metal is 1, and ligand, n means ligand, we can change. The general reaction for the formation of complex is here, metal plus n number of ligand forming the complex MLN. Now suppose concentration at equilibrium of the metal is C alpha, and suppose the concentration of the ligand is NC alpha. C alpha is there, but here is N, so N is here, NC alpha. Now concentration of the complex formed is a C into 1 minus alpha. So this is the concentration at equilibrium. This is the concentration. Now for this reaction, equilibrium constant K, that is stability constant, equals to concentration of product upon concentration of reactant, shown here, and this N go to the power of L concentration term. And now substitute the value. This is C 1 minus alpha, here in place of concentration of M and N, M equals to C alpha, L equal to N C alpha to the power N, because this N go to the power of N C alpha to the power N. Now this is the equation, K equal to, this is the equation number 1, and this equation can be used. In this case, this alpha is the degree of dissociation. Alpha is the degree of dissociation, and this equation number 1 is used to calculate the stability constant value K. And in this equation, what is we required for to calculate the value of K? We should have to know alpha. Alpha is calculated, and C is the concentration, and this is the C alpha N number of molecules. We know all the values. Only alpha can be calculated from the value of EM and ES. So alpha, degree of dissociation, value obtained from the graph, and it is shown here. Alpha value can be determined by using this formula: alpha, degree of dissociation, equal to EM minus ES upon EM. So by using this formula, value of alpha can be calculated. So what is the formula? Alpha is equals to EM minus ES upon EM, where what is EM? EM is nothing but the maximum absorbance in the presence of large excess of ligand, and it suggests that all the metal bonded to the complex. So again, now what is EM? Where EM is the maximum absorbance in the presence of excess of ligand, which suggests that all the metal bonded to the complex. So this is the value of EM. So EM value is known from the graph. We have seen the graph, and ES value also obtained from the graph. And what is now ES? It represents the value of absorbance when the metal and ligands are present in stoichiometric ratio 1:n. So what is ES? It represents the value of absorbance when the metal and ligands are present in stoichiometric ratio 1:n. So this is the slide which shows to calculate the value of alpha. So here this graph shows value of ES and EM. So once we know ES and EM, from this ES and EM we know the value of alpha, and if we know the value of alpha, then put the value in this equation, and value of K, stability constant, for this 1:n composition can be calculated. So here C into 1 minus N, so alpha can be calculated from EM and ES, and by using equation 1 it is possible to calculate the stability constant of the complexes for that particular composition of the complex. So this is the one example is given, simple example of formation of complex EM into NL plus, and to form the complex EM-EL-N. So this is the formula to calculate the degree of dissociation, EM minus ES upon EM. What is EM, what is ES are given here. Now different compositions are there, and metal ligands are present in different composition. When metal and ligand are present in 1:1 ratio, now this is one example, when the metal and ligand are present in the ratio 1:1, 1:1 means metal is 1 and ligand is also 1. So both these metal and ligand are in the ratio 1:1. Then stability constant is calculated by using this equation. So what is the K? K equal to, as we know the equation number 1, C 1 minus alpha upon C alpha to the power N C alpha to the power N. But now here N is 1. So therefore here C alpha. As we have seen the equation, this equation one number we have to use. So here N is 1. So what is C 1 minus alpha upon C alpha? Here N is 1. So C alpha to the power 1, C alpha is here. So equation 1, by using that we obtain this C into 1 minus alpha, C alpha of metal concentration, ligand is also C alpha because N is 1. And that is why we obtain this value from equation 1. Now here this C and this C can be cutted, and what is here? 1 minus alpha here, and here C alpha square. C is this C and C. What is then? C alpha square is there. So this is the equation number 2. This is the equation 2. So this equation number 2 can be used to calculate the stability constant K for the metal ligand ratio 1:1. So if the ratio is 1:1, then it is possible to calculate the value of stability constant K by using the formula equation number 2. This is equation number 2, K equal to 1 minus alpha upon C alpha square. So if we know the alpha and value of C is the concentration, then it is very easy to calculate the stability constant for 1:1 composition of the complex. So this is the equation. This equation is used to calculate stability constant for 1:1 composition of the complex. Now in second case, similarly we can find the stability constant for metal ligand when present in a 1:2 ratio. So in second example, when the metal ligand are present in the 1:2 ratio, metal is 1, ligands are 2. Again now equation 1 we can write here C into 1 minus alpha. This is for metal C alpha, and here 2, N is 2. So here 1:N, the ratio is 1:N, N is 2. So here C alpha 2 into C alpha to the power 2. So this can also be written C 1 minus alpha. This C and here C can be cutted. What is make the square of this? So 2 square 4. Here is a C cube, but now C is cut, so C square is there, and this alpha 2 and alpha cube. So we obtain K equal to, this is the equation number 3. This is the equation number 3, and this equation can be used to calculate stability constant for 1:2 ratio of metal ligand in the complex. When the ratio of metal ligand in the complex is 1:2 and ligands are 2, so equation number 3 shown here in this slide can be used. So K equal to 1 minus alpha upon 4C square alpha cube. This equation is used when the ratio is 1:2 of the complex or metal ligand ratio is there. So this is another equation for this composition. And similarly again now, when the metal ligand compositions are present in 1:3 ratio. So if the ratio is 1:3, in that case again we can use the equation number 1 and substitute the value C 1 minus alpha. C alpha is there here. Now N value is 3. N is 3 and C alpha whole bracket having the cube. So here again this C and C can be cutted, and 1 minus alpha is remain here. 3 cube is a 27. So C cube and C. So C is cutted here and C cube is here, and alpha 4 to the power 4. So this is the equation number 4, and this equation number 4, K equal to 1 minus alpha upon 27 C square C cube alpha 4 is used to calculate the stability constant of the complexes. So in this way, for 1:1 or for 1:2 or for 1:3 ratio of metal ligand, stability constant is calculated by using this different equation 1, 2, 3, and this is number 4. So this is the graph which is plotted between absorbance versus the mole ratio of ligand concentration upon metal or metal to ligand, and this is the alpha which is calculated by formula Em minus Es upon Em, and here this is the Es value and this is the Em value. Em is the horizontal part, and from the point from which it turns, curve turns, so that is the Es. So this is the graph already we have seen. Now there are certain limitations of this theory of mole ratio method, and first limitation of this mole ratio method is stability of highly stable complex cannot be determined. So when there is a limitation of this ratio method, mole ratio method, and first limitation is that the stability of the highly stable complex cannot be determined. So stability which is highly stable, in that case it is difficult to determine the stability constant by using mole ratio method. Number 2 limitation is that in case of very weak complexes, this method fails to give the suitable information like composition or like stability constant is difficult in case of very weak complexes. And third point is that the uncertainty in the values of stability constant as the stability of the complex decreases is also not explained by the mole ratio method. So these are certain limitations of the mole ratio method. So in general, it is a very useful method and very simple to this Mohr ratio method is very simple to for calculating the stability constant of the complex, and it is simple as compared to job method of continuous variation. So Mohr ratio method is easy to apply and can be used to calculate the stability constant for the particular composition of the complex, and composition is like 1:1, 1:2, 1:3, like composition in the complex metal ligand ratio should be different. In that case it is possible to calculate stability constant of the complex.